Well, thanks, Jeff. Hello, everyone. So in this talk, I will introduce sulfur X to you. It is a model for sulfur degassing during magma ascent, and it can also model FO2 change along degassing due to sulfur degassing as well as sulfur and iron speciation change. So in general, sulfur X combines existing CO2 water degassing model with a combined sulfur partition coefficient. So sulfur partition coefficient between vapor and melt basically is the mole fraction of sulfur in the vapor divided by the mole fraction of sulfur in the melt. It models closed system degassing during isothermal decompression, and currently we're not considering the scenario of sulfide saturation. This is in one of our future developments. It is written in Python and available on my GitHub site here. So it comes with two versions. First is the full version, calculates the decompression, degassing of sulfur, water, CO2. And there's another version, calculates the sulfur partition coefficients only with the given pressure, temperature, and composition. So the main input required for sulfur X to calculate decompression degassing are initial water, CO2, sulfur concentration in the melt, the initial oxygen fugacity, temperature, and melt composition. And the main output would be water, CO2, sulfur concentration in both melt and the vapor, and sulfur speciation in the melt, and mass fraction of vapor, melt, plus minus crystals, as well as the oxygen fugacity at each degassing step. So what motivated us in the first place to develop this sulfur degassing model comes from recent melt inclusion studies, specifically on the vapor bubbles inside the melt inclusions. So vapor bubbles can take a significant amount of CO2 out from the melt inclusion. So for example, so these left panel are the sulfur and CO2 concentration from measured in the melt inclusions from Fuego 1974 eruption. The red symbols are from a recent study, Rasmussen et al. 2020, where they actually rehomogenized this vapor bubble back into the melt inclusions using piston cylinder experiments. So compared to the unrehomogenized melt inclusion data from the same eruption, which are shown in the gray symbol here, the rehomogenized melt inclusions showed significantly higher maximum CO2 here. And it also displayed this very nice co-degassing trend between sulfur and CO2, indicating that, at least for this eruption, sulfur might have actually started degassing pretty deep together with CO2. However, when I applied a couple of commonly used degassing model to these data sets, for example, decompress and Solex, neither of them can actually reproduce this degassing trend reviewed by melt inclusion data. Therefore, we wanted to develop a sulfur degassing model that can actually predict the deep sulfur degassing and can be applied to arc magmas. So one of the challenges of developing sulfur degassing model comes from the multivalence of sulfur. It can exist as sulfide and sulfate in the melt, and SO2 and H2S in the coexisting vapor phase. And the transition from reduced sulfur to the oxidized sulfur, the range of FO2 is actually pretty narrow, between FMQ to FMQ plus 2. However, this range of FO2 are also encountered by most of the arc magmas, which are of our interest to model. So because of this speciation change, it actually affects the sulfur partition coefficient between vapor and melt very much. So in the panel B, all the symbols are experimentally constrained sulfur partition coefficients. We can see that for experiments containing sulfide mostly, the KD actually increases as as FO2 increases. However, for experiments containing mostly sulfate, the KD actually decreases as FO2 decreases. And for experiments with a mix of sulfide and sulfate, are shown in these gray triangles, we can see that there is a maximum sulfur partition coefficient between vapor and melt at FO2 around FMQ plus 1. So this complicating change of KD as a function of FO2 also makes it difficult to have a universal partition coefficient model covering the whole FO2 range. So SulfurX dealt with this by dividing the sulfur degassing process into two degassing reactions. For the reduced sulfur, sulfide degasses to H2S, we call it reaction 1. And for the oxidized sulfur sulfate, its sulfate degasses to SO2, and we call it reaction 2. And then I used the experiments containing mostly sulfide, shown in this filled circles, and and containing mostly sulfate, shown by these open diamonds, to calibrate the partition coefficient of reaction 1 and the reaction 2 separately. So then use this KD reaction 1 and KD reaction 2, SulfurX will calculate a combined KD, a combined partition coefficient, using the sulfur speciation in the melt. And this sulfur speciation in the melt can be calculated using some existing models. Currently, there are 3 models available to choose in SulfurX. So this figure shows the composition, pressure, and temperature range of all the experiments used to calibrate reaction 1, sulfide degasses to H2S, shown in filled circles, and reaction 2, sulfate degasses to SO2, shown in open diamonds. So we can see that for the reaction 1, most experiments are basaltic to basaltic andesites, and the pressure range is between 70 megapascal to 300 megapascal, and the temperature range for reaction 1 experiments are actually pretty narrow at low temperature between 1000 to 1050 degrees. And the experiments for reaction 2 have a wider range of composition variations. However, it's mostly still basalt and basaltic andesites, and they also have a wider pressure and temperature range here. So SulfurX is really calibrated to apply to basalt and basaltic andesite system. So in order to go around this limitation of narrow temperature and pressure range, so when we calibrate the partition coefficient for each reaction, instead of regressing empirically for the pressure and temperature effects, SulfurX actually used a more thermodynamic approach. So we used the volume change of each reaction, as well as the fugacity of the volatile vapor in the vapor phase to account for the pressure effect, and we use the enthalpy change of each reaction to account for the temperature effects. So this right panel just shows an example of how predicted KD1 compared to the measured KD reaction 1 for all the experiments. And then this figure is kind of a summary of how SulfurX calculates the combined partition coefficient and how it compared to the experimental data. So here, for a given pressure and the temperature and melt composition, SulfurX first calculates reaction 1, which are shown in these blue circles, and then reaction 2 shown in the purple circles. And depending on the sulfur speciation in the melt, the contribution of reaction 1 and reaction 2 will change. And then this solid line is the calculated combined partition coefficient as change as a function of FO2. We can see that as the sulfate species in the melt increases, the contribution of reaction 1 decreases as the circles getting smaller, and then the contribution of reaction 2 increases as the circles getting bigger. Comparing to the experimental data I showed in previous slides, we can see that this combined KD approach, even though it's pretty empirical, it actually can very well capture this first increase and then decrease shape displayed by the experimental data. It also predicts a maximum KD at FO2 around FMQ plus 1. So at this point, we can take a look at one of the package that calculates the sulfur partition coefficient only. So it's written in Python. You can run this in this manda.py file. So it's very simple. So it basically just reads in a CSV file of all the initial conditions, and then give you another CSV file back, showing all the results of calculated partition coefficients. More details here. So the input, this is an example of an input CSV file. The demo file is already included in the folder. All you need to do is just to copy paste your sample names, your pressure, temperature conditions, and FO2 relative to FMQ buffer, and then major elements composition, water concentration in weight %, and estimated mole fraction of water in the vapor, which is used to calculate the KD reaction 1. So once you done all these, just run the program in the main.py file, and then it will give you back an output file containing the calculated partition coefficient for reaction 1 and 2, and calculated sulfur speciation in the vapor and in the melt by different sulfur ion models, and also different combined KD based on different sulfur speciation models. It also gives you an estimated error for the calculated KDs using the Monte Carlo simulations. Okay, so now let's go to the full version to calculate decompression degassing. So once the combined partition coefficient for sulfur is calculated, sulfur X will partition sulfur into the vapor phase. After that, it will calculate the CO2 and water concentration in the vapor and in the melt using an existing CO2 water degassing model. So the user can choose which model to use. Currently, there are only 2 COH degassing models available in sulfur X. It's volatile calc and Incarno Marziano et al. 2012 model. Then you can also choose if you want to track FO2 change along degassing or just have the FO2 buffered. So the way, if you decide you just track the FO2, the way sulfur X tracks FO2 is that at each degassing step, sulfur X will search for an FO2 that satisfies 3 different equilibrium. So first of all is the sulfur FO2 and the water fugacity equilibrium in the vapor. And then it's the FO2 and the ferric ion equilibrium in the melt, which can be calculated using Kress and Carmichael model. And lastly is the sulfur and ion speciation equilibrium in the melt. Again, you can choose one of these available models in sulfur X to calculate it. So there are 4 unknowns in this system. The last constraint comes from the redox budget conservation in this closed system. So basically that means the total numbers of electrons all the sulfur and ion species need to reach the reference states, which are sulfate and ferric ion here, are always the same. So just then at each degassing step, sulfur X would actually solve for this FO2 iteratively until it actually finds an FO2 that satisfy all the requirements. Okay, so here is how it looks like for the decompression degassing calculation interface. So the first few lines are just a bunch of initial inputs, temperature in Celsius and initial FO2 relative to FMQ buffer, initial water in weight %, and initial CO2 and sulfur in ppm. And then there are a few questions to choose. First, if you like to enable crystallization or no crystallization, which COH degassing model to choose from, and if you want to track the FO2 change or simply buffer it. Scrolling further down, here are the where you can choose different sulfur ion speciation model. And then this sigma is basically the tolerance of the FO2 you want when it calculates the FO2. So this is like one parameter the user can kind of play with if the model fluctuates a lot or it becomes a little bit unstable when it tracks FO2. Maybe it's because this value is too small. You can make it slightly larger to make the model more stable. So the last two parameters are related to how SOFRX take into account of crystallization. So SOFRX does not calculate how melt composition change as crystallization goes like melt does. So we take a very empirical method here of, so first of all, the way we link the degassing process to calculation of mass fraction of melt is using this empirical relation between potassium and the water concentration. So for our example calculation and the default set, this relation comes from the Lloyd et al. 2013, specifically tuned for Fuego magma. And then assuming potassium is a perfectly incompatible element, so one can link the water concentration to get to the mass fraction of the melt. And the vapor, mass fraction of the vapor can be calculated by mass balance of water and CO2. And lastly, the amount of crystals can be calculated using the mass conservative of the whole system. So this really requires the user to have more knowledge of their own system, so they can come up with with this empirical relationship that fits on their own data sets. And because the melt composition also change as fraction crystallization goes, so if you want to take into account the crystallization, the user also have to input this empirical relationship. How does the different oxides change as a function of melt fraction? Again, the default setting written in SOFRX is specifically tuned for Fuego. Okay, so in the end, there is also a line you can actually input, read in a CSV file for your melt inclusion data. So to make some comparison plots in the end, and all the output will be written in a CSV file in the SAM folder. So there is also a README file in the SAM folder containing the information of how to cite SOFRX, which is the manuscript is currently in review in GQ, and also a more detailed documentation of how to use SOFRX and some of the troubleshooting. Of course, if you ever run any into questions of using SOFRX, feel free to shoot me an email. I'm happy to help out and hear feedbacks. Okay, so here is an example of the results of SOFRX when applying to Fuego magma. So all these three colorful solid lines are SOFRX results using different sulfur ion speciation model. We can see that it actually goes through the melt inclusion data pretty well compared to some of the old models like Decompress and Solex. The lower panel is how the predicted FO2 change as a function of pressure by SOFRX, and compared to the decompressed results, which are shown in this dashed line. Okay, to summarize, so SOFRX is actually a model for modeling sulfur degassing during magma ascent by calculating separate partition coefficients for separate reactions. It is available on my GitHub site. Now it comes with two versions, one to calculate the decompression degassing, another one to calculate the partition coefficients only. There are some future development we would like to work on. First of all, is to implement sulfide saturation scenario, which can actually affect the sulfur budget significantly. And second, we want to also implement a function to calculate sulfur isotope fractionation, since we are already calculating sulfur speciation in the melt and in the vapor. And lastly, we would like to implement more available CO2 and water degassing models. So this is particularly important to predict the vapor composition, like CO2 over sulfur ratio, and to be compared to the volcanic gas data. So thanks.
Thank you for that. We've got about 1 minute for questions, but I might extend that to 2 because we're slightly ahead of time. So how do I get rid of, can I see the people? Or no, they'll come up because of the hands. So any questions? Yes, please come up. Ewan.
Hi, Echo. That was an interesting talk. Your plot with the KDs and FO2 and the sulfur X fits, there was like some experiments that were kind of like lower down. Yeah, these like lower experiments with a lower KD that don't quite fit the curve. Is there like a reason for that?
Oh, yeah. So this one curve is calculated like just one composition at one P and T. So the only thing is changing here is just FO2, but this compilation of experiments are actually on different compositions, different pressure and temperatures. So that's all caused the scattered. So particularly this very low, all these open diamonds are actually experiments. They were using quite extreme compositions, like really high alkaline or really high magnesium oxide, and so the scatter is really mainly coming from other different factors. And this figure is really to show that regardless all those variations, sulfur X can actually capture this maximum KD at the intermediate FO2 as the experiments shows.
Cool, thank you.